This is another example where we want to try and get the EMF in the two different ways, the V cross B dot ds way and the rate of change of magnetic flux way. So here we have a rectangular region of space where there's a magnetic field, and outside there's no magnetic field, here or here. And there's a loop of wire. This red is the loop of wire. It's a conducting wire, and it has a width W, and the whole region here has a width 3W. So 3 of these loops can fit in inside this region. But there's only one loop that's moving and with a certain velocity v to the right. So you have a loop moving with a certain constant velocity v to the right. The distance x is the distance between the beginning here of the region to the end of the rectangular loop. So that's what x is. It means that when the loop is at this position, x is 0. Because again, remember, it's the distance between the beginning and the end of the loop. So in this position, x is equal to 0. Position, x is equal to w. Position, x is equal to 2w. Position, x equal to 3w. Position, the loop is outside, and x is equal to 4w. So this is just an idea of what's happening in the problem in general. So we want to get the EMF going around the loop this way using the V cross B dot ds rule, this rule. So you want to go around a closed loop. So first we need to determine the direction of the ds vectors. These are the ds vectors. They're going around this way. And then we have 4 sides. We have the right, we have the top, we have the left, and we have the bottom. So basically you have 4 integrations to do. And it's going to turn out very easy. There's only one integration we need to do, but this is what it would be like in general. So why are these 3 zeros? Why is the term on the top 0? Let's see. V wire is this way, to the right, and the magnetic field is into the page. So V wire cross B is upwards like this. So you can see here the angle between V wire cross B and ds, for the ds vectors on the top, the angle is 90 degrees for the part where there's a magnetic field. And for outside, there's no magnetic field. So in any case, the contribution is 0. For the left, there's no magnetic field anyway here. So V wire cross B is 0. There's no magnetic field. For the bottom, it's the same issue as the top. The ds vector is pointing to the right here, but the V cross B is up. So the angle is 90 degrees for this part. And here there's no magnetic field. So the top, left, and bottom give zeros. So the only thing you need to do is to integrate from 0 to L V wire cross B dot ds. Remember, in general, you put ds to be an element of length. It's always dxi plus dyj plus dzk. In this case, we're only integrating in the y direction, so you only have dyj. And then you let the limits of the integration determine the sign. So the next step to get the dot product between these two things, V wire cross B dotted into the j hat direction, and that will just be, the angle is 0, so it will just be the magnitude of V wire cross B and then dy. So what's the magnitude of V wire cross B? Well, the angle between V wire and B is 90 degrees. So the magnitude of the cross product is the magnitude of the first, the magnitude of the second, times sine of the angle between them. Sine 90 is 1, so you get V wire times B. Now the V of the wire is the same at all points. The magnetic field is the same at all points. So those are constants. So you can take them out of integration. So you end up with integration from 0 to L dy, which is just what? It's just. So the integration is actually very simple to do. It turns out BL V wire. And you expect this result, right? Because when you know that when you have a rod moving in a region where there's a magnetic field, there's a potential difference established across its ends with this value. So we know that we can predict this value in the first place. Okay, what about in this position? When the loop is in the middle, what would the EMF be in this case? Again, you have the right, the top, the left, and the bottom. The top and the bottom, we know that we're going to get zeros because the angle between V wire cross B and ds is 90 degrees. So the top and the bottom, there you get zeros. The left is in the region where there's a magnetic field. So this term itself is not zero. But we're going to show that when you add this term to this term, you get a zero. So let's see how that works. So we replaced the ds by dyj in both cases. Remember, the element of length, you always put it as dyj, and you let the limits determine the sign. So here, for the right part, we're integrating from 0 to L. So you put 0 to L. On the left part, we're going from L to 0. And so that you put L to 0. So we keep the dyj the same, and we make the limits be the ones that determine the sign of the problem. So when you get v wire cross b dotted into j hat in both cases, you get the same thing. So the only difference between these two terms is one is from 0 to L and one is from L to 0. So you can see that when we write one in terms of 0 to L, we can write this as minus integration from 0 to L. You can see that they're going to cancel and give you 0. So when you now add them, you get 0. So there's no EMF in the loop, around the loop. So what about when the loop exits the region? Again, write it in terms of 4 terms. The top and the bottom terms, we know they're going to be 0 because the ds vectors are perpendicular to v wire cross b. So the top and the bottom are zeros. And the right now is in a region where there's no magnetic field. So b is 0 everywhere on the right. So the only term that will give a contribution is the left side. So we write again, the ds is always dyj, and we integrate on the left side from L to 0. We're going from here to here, so we get from L to 0. So let's see what this becomes. It becomes that. We can reverse the sign, the integral limits. So you get minus integration from 0 to L, and then the same thing before, v wire cross b, the magnitude of it is v wire times b. And you can take the v wire and b outside, and then you get integration from 0 to L dy is just L. You get minus BLV. So the EMF turns out to be the negative of it was when the loop was going in. So if you want to plot then the EMF as a function of position of the x coordinate, which is the position of the right side of the loop, when you go from 0 to W, the EMF is positive and it gives you a value BLV. When you're inside the loop, when the loop is completely inside the region where there's a magnetic field, there's no EMF at all. And then as the loop is going out from 3W to 4W, the EMF is negative.